Hello, this is Gus with a tutorial for Desmos Scientific Calculator. I notice when a lot of people are asking for help on their assignments, it looks like that they're doing all their calculations on paper and only going to the calculator here as if it were an actual like handheld calculator. That is to say, like they're typing in all the variables with their respective values at the very end and creating these very long, drawn-out equations all at once in a way that it just seems just has a lot of pitfalls and problems with it. So I want to show how you can utilize the resources on Desmos Scientific to write out functions that can be used again and again and again, especially with repeat problems or problems that are very similar and have very similar methods of solving. Obviously, when I do a test or something like that, I show my work for how I go through the steps of solving the problem. But in terms of actually finding out the value at the very end, I crunch all the numbers in Desmos every time. So here we have this problem, find an equation for the tangent plane of the surface here. First thing I'm going to do is just write out all the known variables. So x naught is -1, y naught equals -1. Here, if you put a letter, that becomes a variable. There's only a few exceptions, like e is defined as the that special number. But here, if I have y, if I type any number after it, it automatically assumes it's a subscript. So it's assigning it as a unique variable. So here, I have y naught, and now y1 is its own unique variable. I can set to something else. If I type xa, this is now the variable x multiplied by the variable a. If I want a subscript x, I do x shift negative, so shift minus symbol, a. Now I have the variable xa. But right now we're not doing that. I could write z naught to -11 because we are given that in the problem. But we can figure that some other way, which is I create a function f which takes inputs x and y, and it equals 7x to the fifth plus 9y to the fifth. And here to get these exponents, I just do shift 6. So here I have y, I press shift 6, and now I have an exponent. I type in 5, and I hit the arrow key to the right to go back down, plus 5xy. And so now if I set z naught again, I just input the function evaluated at x naught y naught, and now I have -11, which we know is correct. So next step, I have to write the partial derivatives of f with respect to x, and then again with y. I could write f subscript x, but I'm not going to do that yet. Right now I'm just going to do f1, and I'll show you why I do that. So that's going to be 35x to the fourth plus 5y. And I always forget, I've done this 10 times now, and I always forget to do it. You have to put in the input. So it's taking in x and y as inputs and putting them in the respective spots in the equation. Now I can do fx equals, evaluated at x naught, y naught, f1. And again, this is going to be a problem. If you're new to this, you're not going to write things out correctly. So take your time. I promise you it gets faster and faster. And and when you're all said and done, it's a faster process. Do the same thing with y now. Equals 45 y to the fourth plus 5x. So now our partial derivative evaluated at the point for y is x naught, y naught. Sorry, it's going to look a little messy me writing this out, but I'll get it right. So at this point, we have our z component of the initial point. We have the partial derivative with respect to x, the partial derivative with respect to y. You could write out the answer if you wanted to. It equals z naught, which would in this case be -11, plus 30x minus -1, which just becomes x plus 1, plus 40y minus -1, which becomes x plus 1. Excuse me, y plus 1. And here you have your answer. This is the correct answer you could write down and get full points for. But we can go a step further than this, because we have a value here, an actual number. We have an actual number here, which can be distributed to this number, and a number here, which can be distributed to this number. So you can end with 3 terms, just a constant term, and then an x term and a y term. So here, we're going to make a capital C, as in constant, equal to z naught minus the partial derivative with respect to x evaluated, or multiplied by x naught, minus fy evaluated, or the partial derivative of f with respect to y evaluated at the point in question, multiplied by y naught. And again, it's important to write out the equation as you see it in the textbook here, because even though this becomes a positive, this term here becomes positive because x naught is -1, and this term here becomes positive because if y naught is -1. But if we change the values up here for different points, then if you put a plus here, because we know it's -1 here, then we're actually going to get a negative out here. So it's very important to write out the equation as you see it in the textbook, and just trust that the variables you input will adjust accordingly. So now we have c equals 59, and now we can write our new equation is just going to be 59 plus 30x plus 40y. And again, this is giving me an error because I'm not actually giving it an input. I wanted to, I could do this. Make a function. And we see that that is correct. Now you might be thinking, this took too long. It's too complicated. I might as well just do it on paper. And I'm going to show you why that's not true. Because now we have a new problem. Find the linearization of the function f x of y equals x y squared at the point -116. We're going to go through all the same steps. X naught is -1, y naught is 16. And look at that, immediately, well, I get a new number here. Obviously, it's not the correct number because I have to put in the new function. But here I already have a value for z naught. And notice we weren't given z naught in this problem. We had to find it ourselves. And without doing any extra work, we've already found it. We find the partial derivative of x with respect to y, which is going to be square root y. Or sorry, yeah, square root y. And look at that. we've already have this partial derivative evaluated at the point in question without any extra work. Do the same thing here for the derivative with respect to y. It's going to be 1 over 2 square root y. And we've already had it evaluated. And look, now we have our partial derivative of x, partial derivative of y, and the constant. So we already have the answer. It's going to be z. In this case, well, it's x y equals 2 plus 4x minus 1/8 y. And that is the correct answer. Do the same exact thing here. It's going to be a little different now because we'll see why in a second. We have this function. Start off by just writing out the function. 25 minus 3x squared minus y squared. X naught is negative 2, y naught is negative 3. What makes this problem different is now everything's under the square root, so we're going to have to use a chain rule. Now, you could just do the chain rule on its own terms, and you're going to get the correct answer, but we have a way to make that much simpler. So we all know for both partial derivatives, it's going to be this derivative multiplied by this derivative, and then this derivative multiplied by this derivative again. To simplify this, we're going to take everything in here and set it equal to a new function called u. So the function u of x and y equals 25 minus 3x squared minus y squared. Okay? Now we can do the partial derivative with respect to x. So the partial derivative of negative 3x squared becomes negative, oh, my lord, becomes negative 6x multiplied by the derivative of u. Now, the derivative is of the square root of u, which we know is going to be 1 over square root of u. Have a 2 here. Oh, my bad. 1/2 square root of u, inverted. I'm saying these things weird, but I trust me it's correct. And look at that. I didn't have to do, it's not all messy, because otherwise I'd have to put this down here, and it's all clean. I do the same exact thing for the partial derivative of y. It's going to be negative 2y multiplied by the same thing again. And I'm done. I am done. I have my partial derivative evaluated at x, partial derivative of respect to x at the initial point, the partial derivative of y evaluated at the point, and I've simplified it down to the constant, so I can write out the equation right now. It's going to be 2.5 plus 3x minus 3/2 y. And what's nice about having written it out in this function form is now I can just do L of negative 2.1, comma 3.1, and now I have my answer. Let's see if this is correct. It is correct. Now, you notice I didn't simplify the function here. So you might not, okay, well, how do I know it's correct or not? Well, I evaluated my function, which is simplified, and got the same answer as this function, which is not simplified, because they are, in fact, the same function. So I hope this helps. Again, I want to show that you save a lot of time and effort just writing everything out in its most basic form from start to finish the first time through, and then it takes very minor adjustments all the way through. Instead of, again, with things like the chain rule, this might look a little complicated because you are dealing with, I could have instead just said, u equal to this, and then just like wrote u here at first. Like, if I were you, I would just write u first like this and do the chain rule with just u, and once everything's set, then add this xy thing here. Because, yeah, the parentheses xy does make it look a little more clunky. So maybe if you're doing this, just do your partial derivative, or do your chain rule on paper, and then plug it in here. Or not. If you find that you really like doing paper for most of it and only want to use Desmos for the very end, if that works for you, that works for you. I just find that this process makes things so much cleaner. And, yeah, I hope this helps.